Hi, everyone. Thank you for that great introduction. It's really nice to be here. I'm glad that you all could make it. Really excited to be here for a showing of Interstellar, and I'm even more excited to be able to offer the prelude for that movie. This is on, right?
It is.
Am I good? Great. Awesome. So, if you were over the age of 30, you were born at a time when we knew of just 8 planets, and they all orbited our sun. And I'm purposefully ignoring Pluto. But fast forward to today, and we now know of more than 5,000 exoplanets, or planets that orbit stars other than our own sun. And since the dawn of humanity, people have wondered about Earth's origin and our place in the universe, and asked many of the questions that you see up here. But up until recently, and thanks to the discovery of many of the exoplanets that we know, it's been impossible to answer many of these questions. But today I'm going to talk about how exoplanets have opened the window of opportunity for answering many of these questions. As I mentioned, the field of exoplanets is very young. The first one was only discovered about 30 years ago, and since we've discovered over 5,000. The recent boom in discovery that you're seeing on this graph as a function of year here is due in large part to 2 very famous space missions, the NASA Kepler mission and the NASA TESS mission. And primarily, while there are over 10 different ways to find exoplanets, just 2 of them are responsible for the discovery of more than 95% of the total planet population. And so they're very important to understand. The first of these 2 methods is known as the wobble method. And it's conducted by measuring the speed of the star as a planet orbits it. So you can imagine that as a planet orbits around the star, it's not totally correct to just say that the planet is orbiting the star. Rather, the star and the planet are orbiting a common center of mass due to the conservation of momentum. Now, what you're seeing here is a scatter plot of data. These are, some of the formatting I think is a little skewed. There's some commas as data points that aren't actual data points. But the point being here that these are real data on a real exoplanet system that I've worked with. And what we're seeing here, this kind of back and forth motion here, which is a measure of the star's motion, is not actually the planet orbiting the star, but rather the speed of the star as the planet wobbles around it. And so by measuring this wobble of the star, we can back out what must be happening to cause that wobble. And in many cases, this is due to a planet. The second of these 2 very important methods is known as the transit method. And the transit method involves monitoring the brightness of a star over time. You can imagine that if you had some star and a planet were to orbit in such a way that it would cross in front of the star, it might block out some of its light. In this case, we're monitoring some star, and while most stars are relatively bright, stars that have planets that cross in front will cause this periodic dip in the brightness, which in this case here you can see is a less than 1% effect. And these are again real data on a real exoplanet system that I've used, taken from the NASA TESS mission. As we let the system play out a little bit longer, we see that again we get another dip. In this case, the data tell us that the time between these 2 dips is about 5.5 days, meaning that a year on this planet is less than 1 week on Earth. That's 16 times smaller than that of Mercury in our own solar system. We let this play out even further, and again, another dip, no surprise, another 5.5 days. This is the planet periodically orbiting around its star. By studying the transit events of these exoplanets around stars in detail, we can learn a lot about exoplanets. And specifically, when using the radial velocity or that wobble method and the transit method in tandem or in conjunction with each other, we can learn a ton about the characterization of exoplanets, namely by way of their mass, their radius or their physical size, and their orbital period. By just looking at the mass and the radius, we can understand a planet's density and infer its composition. So to understand this, imagine a scatter of all known exoplanets in terms of their masses on the vertical axis here and their radii or physical size on the x-axis here. If we plot up all of these planets, we consider that the planets with very small radii are very small in size and high masses. These are going to be more dense. Conversely, planets that have large radii or large physical size but very small mass are going to be less dense, like a gaseous planet. It's often helpful to qualify the planets that we know of in terms of the ones we have in our own solar backyard right here: Earth, Jupiter, Venus, Mercury. When we plot those up and we compare them to other exoplanets, we see that many of them do in fact look like these gassy Saturn and Jupiter-like planets. Very few notice that we know of are rocky and small like Earth. But there are many planets on this graph that we've discovered that don't look anything like what we have in our own solar system. How can you come up with planets that are so massive and not very dense at all? Or how can they be so dense, this planet all the way up here? How do you make some of these planets? There are so many questions just like these that currently we don't have answers for. The orbital period of a planet is also a very powerful characterization tool for understanding exoplanets, because by having the period, or the time it takes a planet to go around or orbit its star, we can directly understand its distance. And the distance is powerful for a couple of reasons. The first of which being temperature. The closer a planet is to its star, the hotter it's going to be. The further away a planet is from its star, the colder it's going to be. Of course, we would like a planet to be in what's known as the Goldilocks zone, which is not too hot, not too cold, but kind of just right, where you could have that liquid water form. Too hot, it's all going to be steam. Too cold, it'll all be frozen over. Got all our planets in now. We also believe that planets form in disks around young stars. And by understanding where in a disk a planet has formed, or the distance that a planet is from its star currently, we can understand how that planet may have formed and how that solar system is formed. And by understanding how other planets have formed and other stars and other solar systems have formed, we can learn a lot about how Earth, our planets, and our solar system has formed. Here's an example, an artist's conception of some interesting planets that we've found so far. And this is an example of a multi-planet system, TRAPPIST-1. This is just an artist's conception, but TRAPPIST-1 is a 7-planet system that we found several years ago thanks to the NASA TESS mission. And this is a great example of something that 30 years ago we had no idea, that 7 planets, just like sort of in our own solar system we have 8, but point being that so many planets could orbit another star. And in addition to exciting multi-planet systems like TRAPPIST-1, we've also found planets orbiting dead stars. We've also found planets that orbit 2 stars at once, which is it's tantamount to Tatooine for Star Wars fans out there. So about 30 or 40, 50 years ago now, however long that movie was released, at the time that was just purely science fiction. They devised some scenario where there was a planet that orbited 2 stars, yet we hadn't even found the discovery of 1 exoplanet. Fast forward, and this is no longer science fiction, it's just science. We have actual planets that orbit, just like Kepler-16b does, that orbits 2 stars. And I'm going to transition this into the movie that we're here today in just a second, but I want you to remember that Tatooine planet. But overall, thanks to a variety of detection techniques and some tremendous advancements in technology, we've been able to build up a census of more than 5,000 exoplanets today, and this number continues to increase exponentially. But we've really just scratched the surface. Because the Milky Way is just one of over 100 billion galaxies in the universe, and in it there's over 100 billion stars. And recent studies show that each star, on average, should have at least 1 planet. So that means that in the grand scheme of things, if there are 100 billion stars, each one should have at least a planet, there might be over 100 billion planets in our galaxy alone, and we've only found 5,000. Our sun is just one of these stars, and all 5,000 of the planets that I've mentioned are roughly within this small red patch on the screen, which means that even in terms of the scope of the galaxy, we've barely even gotten out of our solar neighborhood. So there's a lot of room to grow here, but we've learned so much about what's going on in this red patch. This picture might look familiar to those of you who have seen Interstellar before, but to those who haven't, I'm not going to be giving away too many spoilers, but I did want to introduce the topic that within this movie we're about to see is going to create a scenario where people are exploring a planet that orbits a black hole. And I want to go back to that idea of the Tatooine-like planet that orbits 2 stars, because currently we don't know of any exoplanets that are orbiting black holes. It's purely science fiction. But to think that in 20, 30 years from now we could find planets that orbit black holes, it's quite possible. It's possible that we will. But at the time of this movie, and certainly right now, again, this is just science fiction. But the people the team who created this movie, Christopher Nolan, the director, and then one of the top science advisors, Kip Thorne, put a lot of work into the science that went into Interstellar. In fact, it's been heralded for the last decade about how ahead of its time it was in terms of the modeling of black holes and a lot of the science that went into this. In fact, Kip Thorne here went on to get a Nobel Prize for his work in black holes, much of which was used in the creation of Interstellar. So what you're about to see is very scientifically accurate. In fact, Kip Thorne, there's a great story about how Kip Thorne nearly backed out of the movie at one point because Christopher Nolan, the director, wanted to create some scenario where people were going to move faster than the speed of light, but Kip Thorne said that he would leave the movie if anything broke the laws of physics. And so you can be rest assured that Nobel laureate Kip Thorne stands by all the physics that you're about to see in this movie. And so for the time that it was released, at 2014, I think, this is really a great showing of all the science that we're aware of. Albert Einstein is very famous for his creation and postulation of general relativity, which effectively says that matter bends spacetime, and spacetime tells matter how to move. What you're seeing here are three massive particles, maybe in this case a sun and two stars, or rather a sun and two planets, and their mass actually warps spacetime. And this is a complicated process, and there's a lot of weirdness that comes up when you start to bend spacetime, and time gets funky and wiggly, and everything gets kind of confusing. But to relate it to the movie a little bit, I wanted to make a quick diagram to explain one bit of interesting weirdness that is useful to understand in advance of seeing Interstellar. And that's something known as time dilation. So imagine again that planet that we just saw orbiting a black hole. General relativity tells us that a black hole is going to warp spacetime because it's so massive, it's going to warp it tremendously. And if you place a planet orbiting that black hole, it's going to be subjected to falling into this, what's called a gravitational well. Now these clock diagrams here are meant to illustrate the passage of time. And clocks that are very far outside of the well will run at a very normal speed. But as you get deeper and deeper into the well, this clock runs a lot slower than that is outside of the well. And so you can imagine that a planet that is orbiting a black hole will be subjected to time dilation, and that planet will experience time at a much slower rate than planets outside of it. And this is a really important fact for a lot of the movie that we're about to see. The other really important thing for exoplanets, really the key objective for us into why we want to understand exoplanets, besides just studying what's out there to learn about what's within, we'd also love to find evidence for life, or lack thereof, maybe in the universe. And this is also a key idea in Interstellar. They're looking for planets that are habitable. And so it's important to understand what is the recipe for finding life on another planet. And the first one, at least as we understand it here on Earth, is that we need liquid water. And so I go back to that instance of the Goldilocks zone, where you don't want a planet that's too hot, you don't want one that's too cold, you want one just right, where you can have the liquid water to survive. In addition to just liquid water, you also need sunlight or energy, some form of energy that you can harness for a variety of resources that we, at least as intelligent life, need to survive. You want something that's rocky, so something with a rocky core. A gaseous planet is not something that we, at least as humans, are able to build civilizations for. So maybe you can probe planets for microbial life in gaseous planets, but if we're interested in looking for other planets to visit, as they may do in Interstellar, we'll want something that has a rocky core so that we can stand on it. And of course, we need an atmosphere, something to protect us from high energy particles that are coming through the universe and the galaxy. We need an atmosphere to protect us. It's sort of like a warm jacket that a planet needs to put on to be able to protect it from a lot of things in the environment that is in the galaxy. So liquid water, some form of energy, typically from the star, and some sort of a core and an atmosphere are the things that you really look for a good destination home for another planet. But thinking about exoplanets as a whole, I mentioned that we started this journey around 30 years ago when the first exoplanet was discovered, 1992. So it's been a little over 30 years now. And we've since begun to actually answer many of these questions, the formatting of which is making some of these a bit illegible, but the point being is that only now have we actually been able to answer these questions. And I challenge us all to look forward to some of the things that we'll learn about planets from the next 5,000 that we go on to discover. And with that, I'm excited to introduce the movie Interstellar and thank you all again for your time tonight.